Hello, so we are back with a live class. Today's topic is factorization. So just a reminder for those of you who are new to this stream, we are going to conduct these classes live every day from 6:30 p.m. to 7:30 p.m. That is Indian Standard Time. These classes are for people who want to become better programmers, right? Better at DSN algorithms. So please make sure that you subscribe to the channel and press the bell icon to get notifications, right, about any new videos. As always, there will also be a practice set available to you. Uh, this practice set will have a few problems so that you can apply whatever you learn in today's class, right? Actually practicing the problems will help solidify the concepts. The link for that will be in the video description. All right. So we are going to cover factorization today. Now, factorization is a topic of mathematics. All right. And as computer programmers, you will need to have a decent understanding of mathematics. In fact, in all sciences, and computer science is a science, right? The stronger you are at maths, the easier your life will be. Now, programmers, you don't have to be very good at mathematics, but there are certain areas that you need to focus on to be a good programmer. Now, these topics are like discrete math, probability, statistics, combinatorics, linear algebra, modular arithmetic, number theory, graph theory, right? So it is still a very large section of topics that you will need to be a very good programmer. So we're going to start with that. And today's topic is from number theory, and the topic is factorization. All right. So let us begin. All right. Cool. So before we begin, let us start with a question directly, right? Let us say that you have been given a number n, all right? And this is an integer. This is an integer. In fact, this is a positive integer, right? Your task is to find all the factors of this number, right? So for example, let us suppose that you have a number like 16, perhaps, right? So can someone tell me all the factors of 60? What all numbers is 60 divisible by? So when we're talking about factors, we are talking about the positive numbers, right? The positive integers that divide 60, right? And do not leave a remainder. So what numbers are those? So firstly, we have 1, right? Then does 2 divide 60? Yes, it does. So we have 2. Similarly, 3 divides 60. 4 also divides 60. 5 does, 6 does, 7 does not really divide 60, right? Now 8 also does not divide 60, neither does 9, 10 does, right? 10 definitely divides 60. After that, what numbers we have? So we have 12, right? Then we have 15, then we have 20, right? What more? We have 30 and 60, right? So these are all the different factors of 60. Right? Cool. Now, before we dive further into this problem, let us try to draw some observations. Right? Let us try to draw some observations and see if there is some pattern to what the factors of a particular number are. Right? So first of all, you will notice that 1 and the number itself, they are always factors of this number. Yes, do you agree? Well, 1 divides every single number. And if you have a number, let us say n, then that number will divide itself, right? So that has to be a factor. What else do we notice over here? Is there any other pattern that we notice over here? Yes? So we notice one more thing. So the first thing is that 1 and n are divisors of n. The second thing that we notice is that factors come in pairs. Factors come in pairs. What do I mean by that? I mean that given any factor, there is a corresponding factor. Right? So if I pair 1 with 60, then I will get 60, right? 1 times 60 equals to 60. Similarly, if I pair 2 with 30, then I once again get 60. So 2 times 30 is 60. Similarly, 3 times 20 is 60. 4 times 15 is 60. 5 times 12 is 60. 6 times 10 is 60, right? And then if I continue from here on, you will see that I will just repeat these things, right? So I will just repeat these things. I will say 10 times 6 is 60, right? So 10 and 6 have been repeated. Similarly, I will next say 12 times 5 is 60. So after all this, the numbers are being repeated. Is that clear? The factors will always come in pairs, right? That is the main observation that we draw from here. All right. Now, given that we have these observations, could we write a program? Could we write a function, let us say find factors, right? That takes an integer n, and let's suppose prints out all the factors of n. So let us in fact call this, instead of find n, let us call this print factors, right? This function accepts an n, and it is supposed to print out all the different factors of n, right? So what approach do we see over here? So one way to do this would be the naive way, right? The very simple way. The first way would be to go through all the numbers, go through all the possible divisors, right? So to go through all the possible divisors, we will need a few more observations, right? Let us quickly see what those observations are. So the first observation was that 1 and n are divisors of n. There is one hidden observation over here, right? Let me mark this as the third observation. And that observation is there are no divisors that are less than 1, and there are no divisors that are greater than n, right? So the divisors, so 1 is the smallest divisor and n is the largest divisor. Yes? Does that make sense? So when I am trying to find the divisors of a particular number, I only have to go from 1 all the way till n, right? Because I cannot have divisors that are greater than n. Does that make sense? Is that part clear? Right? Perfect. So how do we write this program then? This is a very simple for loop. So we will say for I goes from 1, right, all the way till n, and we'll increment I. So we'll go through all the different numbers. What we will do inside this? We will check if n mod I equals to 0, right? So everyone is familiar with this mod operation, right? This is the remainder operation. This says that when we divide n by I, then what is the remainder? Is that remainder 0? If that remainder is 0, then I must be a factor, right? I must be a factor. Then what do? We simply print I, right? So this is our code for factorization, right? Cool. Now this is the first approach. This is very naive. We can do much better than this. But why is this naive? So let us analyze the time complexity of this particular program. So how much time does this take? If I have a number n, then what is the time complexity of this particular program? Well, this is a simple for loop, right? We are going from 1 all the way till n. So this is linear. In fact, this takes order of n time, right? Cool. Can we do better? Well, certainly we can. So the first thing that you will notice over here is that whenever you are looking at these numbers, we know that the largest factor is the number itself, right? The largest factor is the number itself. But what is the second largest factor? How big can the second largest factor be? So I know that the largest factor is n itself, right? What about the second largest factor? That must be less than or equal to n by 2, right? That factor must be less than or equal to n by 2. Why? Because if it is greater than n by 2, then its corresponding pair, right? Divisors always come in pair, right? Factors always come in pair. Its corresponding pair will not be an integer, right? 2 is the smallest integer that might divide this number apart from 1, right? So we know that the second largest has to be less than or equal to n by 2. So one thing that we can do over here right away is, instead of having this loop from 1 till n, right? We can modify this, right? So let me just modify this over here. I will say I is less than or equal to n by 2, right? And notice that this is integer division over here, integer division, right? So in this loop, I will print all these divisors, but now I do not print n, right? I have missed n now. So I will have to add another statement over here, which will simply say print n. Is that clear? Because now our loop is going from 1 all the way to n by 2. So I will not print out n in this loop. I'll have to print it separately. Yes? So how much time did we save just now? We made our program twice as fast, right? That's very nice, right? We certainly made our program twice as fast. Asymptotically, it is still linear, right? It is still order of n time, but practically it is twice as fast, right? Perfect. All right. So can we extend this? Can we extend this observation further? What about the third largest factor? What about the third largest factor? How large can that be? Well, if the number is divisible by 3, then the third largest factor can be up till n by 3, right? Does that make sense? So third largest factor has to be at max. It has to be less than or equal to n by 3. Similarly, the fourth largest factor has to be less than or equal to n by 4, right? And so on. So we see this pattern over here. Is that clear? Cool. Now the question is, we could use this particular observation to reduce our time complexity by half. How do we utilize all these observations? How do we really utilize all these observations? So to do this, let us make one more observation. Right? Let us actually go back to this observation that we had previously. Let us look at this thing once again. Okay. So let us say that instead of going from 1 all the way till 60, right? Instead of going from 1 all the way till 60, we only go till this midway point. Right? You clearly see that there is this midway point over here. After this midway point, so this is the midpoint. After this midpoint, the numbers will repeat. Yes, 6 into 10 repeats as 10 into 6. 5 into 12 will be repeated as 12 into 5, and so on. Right? So we only need to go till this particular point. We only need to consider this half. We do not need to consider the other half. All right. So if we are considering this half, then we have to go from 1 all the way till what number? We have to go from 1 all the way till this number. How do we find what this number is? How do we find what this number is? So basically, we are looking for a number I, right? We are looking for a number I such that I times something else. First of all, this should be equal to n, right? Because they are numbers, they are factors, right? So I times something should be equal to n. Secondly, I am looking for a number such that I is less than or equal to this something, right? Because so basically, I'm going till 6 because the pair of 6 or the number which is paired with 6 is greater than 6, right? 10 is greater than 6. If I go any higher, then the numbers will swap. 10 will now become, the first number will become greater than 6 now, right? So we are looking for a number over here that follows this property. Okay, so if this is x, then what can I say from here? I can say that x equals to n divided by I, right? So I can put the value of x over here. I will get I is less than or equal to n divided by I. What can I get from this? I can move this I to the left hand side, right? So I will get I squared is less than or equal to n. And what does this tell me? This tells me that these numbers, they must be less than or equal to. So I must be less than or equal to square root of n. Is this part clear? Is this derivation clear? This is very simple. A lot of you might already know this, but it is important from where this is derived. Right? This square root sign, this is not magic. All right. So once again, we are saying that we are looking for a number I, we are looking for a factor I, such that its paired factor, when we multiply them, we get n, right? They are factors. Now we are also saying that, okay, we are going to make sure that this factor must be less than or equal to its pair. Right? This factor must be less than or equal to its pair, because if it is greater than its pair, then we are just repeating ourselves, right? Because 2 times 3 is the same as 3 times 2. So we only need to make sure that this number is smaller than this number. Otherwise, we will be repeating ourselves. So we put this in the equation. We say I is less than equal to n by I, which means that I square is less than equal to n, which means that I is less than equal to square root of n. So what did we get from here? So now we can improve our program. We can now say that we have a for loop for I equals to 1, I less than square root of n, right? Square root of n and I plus plus. I less than equal to square root of n and I plus plus. All right. Now I will check if in fact n is divisible by I. So what should I print over here? If n is divisible by I should print I, right? I should print I. But is that all? Is that all? No, because I also have to print the other pair, right? Remember, we are only going from to half the pairs now. So we also have to print the other pair. So I will also print n divided by I, right? N divided by I, right? And that will complete the list of factors. Is this part clear? Right? Is this part clear? Yes. Perfect. Right? Now, first of all, there is a mistake in this program. There is a mistake in this program, a very subtle mistake. Can someone point that out? Yes. Exactly. So over here, let me just point it out. So over here, Lucky says that, hey, this is the mistake, right? What happens when I is actually equal to n by I? Which means that when n is a perfect square, you will be printing this number 2 times, right? That is not very good. You will be printing this 2 times. That is not very good. So how can we fix this? Right? So first of all, is everyone clear? If n is 9, n equals to 9, what we will see? We will see I equals to 1. We will print 1, 9. Right? I equals to 2, we will not print anything. I equals to 3, we will print 3, 3. Right? So we see that we printed 3 2 times. That is not a good thing to do. Right? So we need to resolve this. And we see that this only occurs when n is a perfect square. Right? Otherwise, this issue cannot occur. Right? So how do we resolve this? We simply say that I goes till less than square root of n. Right? I goes till less than square root of n. And after this, we will specially check. After this loop is over, we will check. So after this loop, what will be the value of I? It will be exactly square root of n, if it exists. Right? So we will say if n mod I equals to 0, then print it just once. Right? Print it just once because it is a square root. So just print I. Right? Notice that we are not printing the pair over here. Is that clear? Cool. So this will give us the correct answer. Now the question is, how much time did we save? What is the time complexity? What is the time complexity of this particular code? Yes. So who can tell me that? Well, this is very simple, right? Just like the previous case, we have a simple for loop. And this for loop now goes from 1 all the way till square root of n. So the time complexity is supposed to be order of square root of n. Right? Simple. Is that clear? There is one more thing over here, that if you were actually using a function to calculate the square root of n, you would not do this again and again. Right? You will actually say sqrt or square root equals to, you will calculate the square root of n outside. And then you will just use that variable. Right? So that whenever you hit this condition, you don't have to calculate it again and again and again. Okay? So this will give us the correct code. And the complexity will be order of square root of n. Now that is a huge improvement. Right? That is a huge improvement, going from order of n to order of square root n. This is huge. This is massive. Imagine that you had a number which was, let's say, 100 trillion. Right? 100 trillion. So if 100 trillion is how much? 100 trillion is how much? It is 10 to the power 14. Right? If you were to check this number, if you were to check a number of this order of magnitude on your computer, it will take a lot of time. Right? How much time will it take? It will take around 10 to the power 5 seconds. Right? Or you can say it will take around 30 hours. It will take around 30 hours of time. Whereas with this particular algorithm, how much time will it take? It will take just 10 to the power 7 operations. So this is 10 to the power 7, square root of 10 to the power 14 is 10 to the power 7. So it will just take how much time? It will take 0.01 seconds. Right? That is amazing. We went from a program that took 30 hours to a program that ran in 1/100th of a second. All right? Cool. So this is how we would factorize a particular number. Okay. So I hope this is clear to everyone. Now let us move on to a question, right? To a question, related question. Okay. Suppose that we have 100 doors, right? And all these doors are closed. All are closed. So we have basically door number 1 over here, door 2, door 3, door 4, all the way till 98, 99, 100. Right? We have all these different doors, and initially all of them are closed. So let me say that these are closed. Okay. Now we are going to play a game. We are going to play a game. This game will have 100 steps because we have 100 doors. We will have 100 steps. So the first step, in the first step, what will we do? We will toggle all the doors. Right? So you understand what toggle means, right? Toggle means that if it is open, you close it. On the other hand, if it is closed, you open it. Toggle basically means to flip it. Right? Cool. So we will say that in the first step, we will toggle all the doors. In the second step, we will toggle all the doors, all the even doors. Basically, we will toggle every second door. Every second door. Right? In the third step, we will toggle every third door. And so on and so forth. It will continue like this forever. In the 100th step, we will toggle. So there will be just 100, right? We will toggle the 100th door. Right? So this is what we are going to do. Is this part clear? So first of all, what happens after the first? So what happens after the first step? Initially, all of them are closed. After the first step, all of them will be open. Right? Then what will happen? After the second step, we will toggle this every second door once again. So this door will become closed. 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 Right? In the third step, we will once again toggle every third door. So this third door will become closed. There was a sixth door over here. Right? It was initially closed. So we will open it up. Right? And so on and so forth. Does that make sense? So we are doing this thing. That is the game we are playing. The question is that after we are done with this game, after 100 steps, which doors remain open? All right. Is the question clear? Yes, after the third step, we will toggle every fourth. So in the fourth step, we will toggle every fourth door. In the ith step, we will toggle every ith door. Right? And the question is, after all these 100 steps, which doors will remain open? Okay. All right. So, I mean, this 100 is a very, very large number, right? So let us actually reduce the problem. So whenever you have a difficult problem, you try to check that problem on smaller numbers, right? So let us say that we only have 10 doors. Okay, we only have 10 doors. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Initially, all of them are closed. Okay, what happens after the first step? So this is the 0th step. This is step 0. Step 1, step 2, step 3, step 4, 5, 6, 7, 8, 9, 10. Right? What happens after the first step? After the first step, every door is open. Right? After the second step, what happens? After the second step, what happens? So after the second step, 1 is open, 2 is closed, 3 is open, 4 is closed, 5 is open, 6 is closed. Right? 7, 9, these are closed now. What happens in the third step? In the third step, 1, we do not change it. 2, we do not change it. 3 was open, right? 3 was open, so we will close it. 4, we do not touch it. 5, we do not touch it. 6 was closed, so we will open it. Right? 7 we do not touch. 7 remains as it is. 8 we do not touch. 9 was open, so we will close it. 10 we do not touch. Yes? Okay, we move on. So in the fourth step, we will keep 1. We will not touch this. We will not touch this. This was closed, so we will open it. We will not touch this. We will not touch this. We will not touch this. This was closed, so we will open it. We will not touch this, and we will not touch this. And so on and so forth. So can someone see what is happening over here? Can someone see what is happening over here? Basically, what happens in the ith step? What happens in the ith step? Exactly. So Srinivas has the right idea over here. Srinivas says that in the ith step, all the doors that are divisible by I get toggled. Right? That is the problem over here. Now the question is, let us suppose that I am talking about the nth door. Right? Let us suppose that I am talking about the nth door. For which all numbers, for which all steps will toggle this door? Will toggle this door. Right? So is the question clear? If in the ith step, I toggle every ith door, then given a door number, right? Given that, I am saying that, okay, let's talk about the 20th door. Right? Let's talk about the 20th door. Then in which all steps will this 20th door be toggled? In which all steps will this 20th door be toggled? All the factors of n. Exactly. Right? All the factors of n. Yes? So basically, 20th door will be toggled in the first step, in the second step, fourth step, fifth step, 10th, and 20th step. Is that clear? Yes, because these are all the factors of 20. Cool. So, how many times will this door be toggled? How many times will this door be toggled? Well, we already know that factors come in pairs. Right? Which means that if there is a step number 1 on which this is toggled, there is also a step number 20 on which there is toggle. Right? Similarly, for step number 2, we have step number 10. For step number 4, we have step number 5. Okay? So we know that the nth door will be always toggled, an even number of times. Right? Because why is this true? Because the factors will come in pairs. Right? So every door is going to be toggled an even number of times. Is that correct? Well, not so fast. Is there any particular number which has an odd number of factors? Right? What happens? So you have this pairs coming up. Right? You have these pairs coming up. What if there is a middle value? What if n is a perfect square? In that case, this value root n, it doesn't have a pair. Right? Root n is going to pair with itself. So it will not have a pair. So basically, if the nth door, so if n is a perfect square, right? If n is perfect square, then nth door will be toggled an odd number of times. Right? In all other cases, it will be toggled an even number of times. Is that clear? Yes. All right. Cool. So what happens if you toggle a door even number of times? Initially, it was closed. Then it became open. Then it became closed. Then it became open. If we do this an even number of times, what will the end state be? It will be closed. Right? Because we started with closed, we toggled it even number of times. So eventually it will be closed. On the other hand, when n is a perfect square, we will toggle it odd number of times. So what will be the final state? We started with closed, we move to open, we move to close. Since we will do this odd number of times, the final state will be open. Right? So which all doors will be open? Now we know the answer. Which all doors will be open? All the doors whose numbers are perfect squares. Right? And in all the doors from 1 to 100, which all doors are those? Which all doors are those? So that is 1. Then 4, 9, 16, 25, 36. Then what do we have? 49, 64, 81, and 100. Right? Exactly 10 doors will remain open, and all these are the doors that will remain open. Is that clear? Yes. If n is prime, then answer will be odd. No. If n is prime, the answer will be even. So Vishwajit has a question, or not this. Vishwajit has a question over here. Vishwajit says that if n is prime, then how many factors does it have? Well, for any prime number, it has two factors, right? 1 and n itself. So for prime numbers, it will be even, not odd. Only for perfect squares. Only for perfect squares will we have odd number of factors. Odd number of factors. All right? Cool. Okay. So what did we learn from this particular problem? This was not a very difficult problem, right? This also does not involve a lot of programming. We did not do anything fancy. We did not do any fancy maths over here. All we did was we sat down, we made some observations, right? We made some observations. We looked at the problem, we tried it with a smaller number. Instead of going to directly 100, we tried it with a smaller number. So that is something that you have to keep in mind, right? Whenever you are facing a problem, whenever you're facing an algorithmic problem or any problem in life, please, your first step should not be to come up with a solution. That is a very, very wrong way of doing things. The first step should be to make observations. Make observations. Right? Once you do this, only then you will be able to find a solution. Find a solution. If you do not make observations, you will never be able to find a solution. All right? So please do not skip this step. Okay. Cool. So that was a nice little exercise. Let us go back to what we were doing earlier, right? So first of all, what we did was we found all the factors. Found all the factors of n, right? That is the first thing that we did. Now, while we were doing this, we kept talking about something, right? We kept talking about prime numbers. So first of all, can someone quickly tell me what a prime number is? So what is the definition of a prime number? What is the definition of a prime number? A prime number, so first of all, it has to be a positive and it has to be an integer. Right? It has to be a positive integer. Secondly, it must have exactly two divisors. Right? It must have exactly two divisors. There is a lot of people think that this is the definition of prime numbers, right? A lot of people think that a prime number is a number which is divisible by 1 and itself. Right? By 1 and itself. If this was the definition of prime numbers, then 1 would be a prime number. Right? Then 1 would be a prime number because, hey, 1 is divisible by 1 and 1 is divisible by itself. But 1 is not a prime number. All right? Is that clear? So this is not the correct definition. This is very close, but this is not the correct definition. The correct definition is that it must have exactly two divisors. Exactly two distinct divisors. Right? So can someone very quickly tell me what the prime numbers are? A few prime numbers from the start. So is 0 prime? Is 0 prime? No, it is not. Is 1 prime? No, it is not. Is 2 prime? Yes, 2 is prime. 2 is the smallest prime number. Then 3 is prime. 4 is not prime. 5 is prime. 6 is not prime. 7 is prime. 8 is not prime. 9 is not prime. 10 is not prime. 11 is prime, and so on. Right? How many prime numbers are there? How many prime numbers are there? 100, 200, 500, 1000, million, billion. How many prime numbers are there? There are infinitely many prime numbers. Infinitely many prime numbers, right? Everyone knows this? Cool. There's a very simple proof for this as well. All right. Okay. So now that we know the definition of a prime number, some people are saying 4 prime numbers are there. That's nice. Suppose now that we know the definition of prime numbers, can we write a program? Can we check if a number is prime? Right? So we know that the definition of prime number is a number which has exactly two divisors and it is a positive integer. So given a number, can we check if it is prime? So is prime, right? It is going to return a boolean and it is going to take an integer. Yes. So how can we write this program? So very simple, right? Very simple. We can say that count is 0, right? We can write a loop for I equals to 1, I less than equal to n, I plus plus, right? And we can check if n mod I equals to 0, then we will do count plus plus, right? And finally we will return what? If the count is exactly equal to 2, then it is prime, otherwise it is not prime. Yes? Right? Cool. What is the time complexity of this program? What is the time complexity of this program? This program runs in order of n time. We already know that we can optimize this a lot. Right? We already know that we can So Suraj says, why Boolean? So this is prime will return true or false, right? It will return true or false. True if the number is prime, false if it is not. Right? Which is why we are returning a Boolean. So TechGeos is asking, sir, just confirming, is this code Java, right? So this might not exactly be Java. For example, in Java, you will have to put a semicolon over here, right? I'm not sure if you write bool or boolean in Java. I kind of forgot, but the rest of it pretty much looks like Java, right? Pretty much looks like Java if we add these semicolons. This will also work in C++, almost exactly the same way, right? However, when we are doing these classes, we will not be following any particular programming language. If you have any questions of a particular programming language, that let's say if you want to ask, okay, so how will I do this in Rust, or how will I do this in Haskell, or how will I do this in, let's say, Python, right? So you feel free to ask that. Okay, feel free to ask that. I will be able to give you an answer for most common programming languages. However, we will not be focusing on the programming language in this particular class, right? We will be focusing on the pseudocode. We will be focusing on the intuition. Okay, cool. So just give me a second. All right. Okay. All right. So we see that this is linear in time, but we already know that we can improve this a lot, right? So how can we improve this? Instead of going from 1 to n, we can go from, so if 1 is a factor, right? If n is a factor, right? And prime numbers have exactly 2 factors. What does this mean? What does this mean? This means that if n is prime, if n is in fact prime, then it must not have any factor, between 2 all the way till n minus 1. Yes? Is that clear? It must not have any factor between 2 all the way till n minus 1. In fact, it must not have any factor between 2 all the way till n by 2. In fact, we can even generalize this and we can say that a prime number does not have any factors between 2 all the way till square root of n, right? Because we see that the factors will come in pairs. Right? The factors will come in pairs. Is that clear? So we can improve this code a lot. We can say Boolean is prime, right? We have an integer n, and we will say, so now we don't need that count anymore, right? Because we are just checking if there is a prime factor or not, if there's a factor or not. So we can say for I goes from 2 all the way till square root of n, I plus plus, right? If there is any factor, if n mod I equals to 0, if we did find a factor, then what can we say? If we did find a factor, then what can we say? Hey, we found a factor, so it must not be prime. If you found a factor between 2 and square root of n, it cannot be prime. So we'll just return false. Return false over here. Right? And after this loop is done, we will return true. Because if we did not find any factors except for 1 and n, then the number must be prime. Is this clear? And the time complexity of this code is? The time complexity of this code is order of square root of n. Right? Perfect. So we know that we can check if a number is prime in order of n time as well. Now, one question, it's not, I mean, we are not going to teach that today in the class, but one very common question is this the fastest we can do? Is this the fastest we can do? And the answer is no. The answer is no. In fact, primality testing, this is in P, right? This is in P. P stands for the polynomial time algorithms, right? I'm not sure if you have heard of P versus NP, right? But primality testing is in P. That means that we can check for primality in log n time, right? In order of log n time. All right, we will not be going over this particular algorithm today. So there are several algorithms. One of the most famous ones is the AKS primality test, right? Okay, but primality can be checked in order of log n. It is in P, right? And no, this is different from sieve of Eratosthenes. Right? This is different from the sieve algorithm. This is a different thing. Okay. So if someone asks you how much time does it take to check if a number is prime, the answer is log n. Right? You can test primality in polynomial time. Okay. Cool. Vikas says, what if n equals to 5? So Vikas has a question over here. Let us look at this code and see what happens when n equals to 5. Does this code work correctly? Right. So let us try that. So what happens? So first of all, we will say I equals to 2, right? So we will first come over here. We will check I equals to 2. Then we will move on to the condition. We will move on to this condition, right? That is how a for loop works. We initialize, we check the condition, we go inside the block, we increment, and we check the condition again, right? So we will check this condition. Well, what is the square root of 5? The square root of 5 is? Well, the square root of 5 is 2 point something, right? Let us suppose that we are doing integer things over here. So we will say that, okay, this is 2 is less than equal to 2.5, right? Less than equal to 2 point something. So we will go inside, right? We will go inside. We will check. Is n divisible by 2? Is 5 divisible by 2? No, it is not, right? So we will continue the loop. We will increment I. So I will now become 3. Now once again we will check. Is 3 less than equal to square root of n? No, 3 is not less than equal to square root of n, right? 3 is greater than square root of n. So we will exit this loop and we will return true. So we will say that yes, 5 is prime, which is correct. Okay. Santosh says, okay, so there's another question. Santosh says that, okay, what if we check with n equals to 2? Right? What happens when n equals to 2? Won't this program return false? Let us see, right? So when n equals to 2, we start, right? We start with I equals to 2. Right? Then we move on to the condition. We check if 2 is less than equal to square root of 2. Is this true? Is 2 less than equal to square root of 2? No, it is not true. Right? This is not true. So it will directly come outside the loop. Okay, it will directly jump outside the loop. It will not go in the loop. And we will return true. So even for true, we will return true. Is that clear, Santosh? Yes. But this program is not 100% correct. This program is not 100% correct. Can you tell me one value for which this program will fail? Exactly. So I use have the right idea over here. What if n equals to 1? Or what if n equals to 0? Or what if n equals to minus 100? Right? For all the numbers that are less than 2, we will never go inside this loop. So we will automatically return true. Right? So we need to improve on this program. We need to add a check over here. Right? So let me just insert some space. So we will very quickly, let me just clear up the mess. This was square root of n. So we will add a check over here. We will check if n is less than or equal to 1, then we simply return false. Right? We simply return false. All right? Is this clear? No, this is not a base case. Base case happens when you are in a recursion. Right? Base case, we talk about base cases when we are in a recursion. This is a edge case. This is a boundary condition. Okay. Sujit, it's almost the same, but it is better if we follow the correct nomenclature. Okay. So base case is when we talk about recursion. Currently, we're talking about edge cases or boundary condition. All right. Yes, we can also say that this is less than 2. Right? We can, instead of saying less than equal to 1, we can also say less than 2. That is perfectly fine. All right. Okay. Let us continue. So now we know how to check if a number is prime. Now a very common question comes up. Let me just check how we are doing on time. All right. So a very common question comes up now, which is called if you had to find all the primes till n. Right? So I give you a very, very large number n, let us say 1 million. Right? And I ask you, find out all the primes till 1 million. Right? How will we do that? Is the question clear? We have to find all the primes till 1 million or some number n. So one way of doing that is to very simply go through all the numbers and check if they are prime. Right? So we can simply do for I equals to 1, I less than equal to n, I plus plus, right? And we will say if is prime. If is prime of I, right? So this is prime is the function that we have coded earlier. Right? This is prime is the function that we have coded earlier. We will simply print I. Simple enough? Yes. How much time will this algorithm take? How much time will this algorithm take? Well, this is prime function. This takes order of square root of I. Right? This takes order of square root of I. And we are doing this thing n times. Right? We are doing this thing n times. So how much time does it take? It definitely takes, it is bounded by, it is upper bounded by, so the time complexity of this program is upper bounded by order of n times square root of n. Right? N times square root of n. It is a little lesser than that, but as importantly, this is what the type bound is. Okay? Cool. Can we do better? Now the question is, can we do better? This was the simple approach. We had the program, we had this function is prime that we have already coded, right? And we simply say, okay, let us go through all the numbers and let us check them. So this will take this much time. The question is, can we do better? All right? Cool. So the answer to this is yes, right? In general, yes. There is something called sieve algorithms. Sieve algorithms. All right? And there's a lot of different sieve algorithms. So one of the most famous that you will come across is the sieve of Eratosthenes, right? The sieve of Eratosthenes. And this is how you pronounce the name. You say Eratosthenes. Okay? Eratosthenes. So this sieve algorithm can achieve much better time complexity. All right? Now, let us just see how much time we have. We are already at 7:18. So let me not continue the sieve of Eratosthenes today. Let us continue this particular thing in tomorrow's class. All right? We are going to keep the today's class simple enough because you will have a lot of practice problems that you can go and try. All right? So let us not continue with the sieve of Eratosthenes today. We will talk about this sieve algorithm tomorrow. And this is a very elegant algorithm. This is a very nice algorithm. It is also very simple to code. Right? So it only has like 5 to 6 lines of code, and that gives you a very powerful algorithm that checks, that finds all the numbers, all the prime numbers up to a given number. All right, cool. So one thing that Ankush is pointing out over here, not this. Where did that comment go? Interesting. That comment just vanished. Yes. So Ankush is pointing out over here that in this particular program that you wrote, right? In this particular program that you wrote this loop as I equals to 2 all the way till square root of n. We can rewrite this in this manner as well, right? So I'm just pointing it out over here, as Ankush said, that these two loops are equivalent. I equals to 2, I is less than equal to square root of n, right? I plus plus. This loop is the exact same as this loop for I equals to 2. I times I is less than equal to n, right? I plus plus. Okay, so instead of calculating the square root of n and then comparing it with I, we square I and then we compare it with n. Right? It will work exactly the same. And this is one more way that you can do it. If you were to do it this way, then you will have to pre-calculate the square root of n, right? You will say square root of n equals to, you will use some sort of a math library. You will say math.square root of n and things like that. So if you do not want to do that, you can simply use I into I is less than equal to n. All right? Bridge says, but don't we have to check for overflow? Well, not really, Bridge, because I into I will not overflow, right? If I into I overflows, then n itself should overflow. Does that make sense? We are not really considering the overflow case over here. We're talking about not too big numbers. Okay, we are talking about numbers that will fit in the integers. Now, if n fits in your memory, if n fits in let's say a 64-bit integer, then I into I will also fit in 64-bit integer. All right. Okay, so let us basically end this lecture. Now, once again, you have a practice set. All right, so please look at the link in the video description. There's a link to practice problems. Please go ahead and try those practice problems, because unless you try them, the concepts will not be solidified. Once you actually sit down, code these things to yourself, right? Once you actually write the program, debug it, test it, then you will be able to solidify all these different things. Okay. Srinivas says, sir, how to deal with very, very big numbers? Well, Srinivas, there are a lot of different ways that you can tackle big numbers. One very common approach is to use a big integer library, right? Big integer library, right? But usually this is not a very good approach, right? First of all, the question is, why would you need to deal with big numbers, right? If you are implementing, let us suppose, some sort of an RSA algorithm, and you want to check if a number is prime or not, then you might have other ways of generating large prime numbers. Right? In practice, we don't really have to deal with we don't have to check very large prime numbers with something like a sieve. Right? With something like a sieve, we don't do that. Okay. All right. So let us end the class. Once again, please subscribe to the channel, hit the bell icon so that you can be notified of the videos. We are going to have this class every day from 6:30 p.m. to 7:30 p.m. Right? And in the next class itself, we will be going over prime numbers once again, and we will be going over a lot of different things. So we have to cover GCD, so greatest common divisor, Euclid's algorithm for that. We have to cover model arithmetic and a lot of different topics. All right, so please make sure that you subscribe to the channel, hit the bell icon, and please go and practice the problems. The link will be in the video description. All right. Cool. If you have any further questions, if you want any other help, then there is also a link to a chat, right? To a chat, scalar discussion. Right? The link for this is also in the video description. If you go over there, you will be able to find the lecture notes, and you will be able to talk to your peers. So everyone who is currently live on YouTube, all the students who are currently enrolled in Scalar Academy, all the instructors that are there, all the TAs that are there, you will be able to interact with them. And if you have any questions, we will be able to help you out. All right. Binu says, sir, please make the class 2 hours. Well, Binu, not right now. I mean, this is YouTube, right? So the attention span, we cannot really expect attention span to be very large. So in the Scalar Academy, we have classes that are 3 hours long, and we make sure that we capture the attention and the classes remain very fun. But on YouTube, we can't really extend it past 1 hour. All right. Is this competitive programming series? This is kind of, so we will be talking about a lot of competitive programming over here, right? So Vinal has the question, is this competitive programming? Well, we will be doing a lot of competitive programming type questions over here, but this is more than that, right? So at Scalar, basically we teach students how to become full-fledged engineers, right? We talk about how to behave in a company. We talk about how to scale applications. We talk about system design, low-level design. Competitive programming and algorithms and data structures is a very small part of that. But of course, we do cover that in depth as well. All right. Cool. So let us end the class then. All right. Bye-bye then. See you tomorrow, guys.